Okay, so we are looking at gate revision. And today we are going to look at gate bioinstrumentation. So this is specific to gate BM. Okay, so I noticed this is one of the most weighted subjects. Not just most weighted. This is actually the most weighted. Okay, most weighted, most important. And technically, with this one subject, with one subject and aptitude math, you can clear the cutoff. Okay, and if you want to do reasonably well, this is a required subject. Nice thing is, so once you understand the concepts, okay, the PVQs kind of are all from a small subset from the entire syllabus, okay. That 80% of questions from 20% of the syllabus is most applicable to this, okay. Specifically, you can say that very well. Whatever is shown here, this is really vast. Despite that, the questions certainly are clustered, and because of that, this is most predictable. Questions are predictable, concepts are certainly predictable. Okay, so if you properly prepare for this, then this also kind of becomes easily scoreable. If you score well in this one subject, you're not first of all worrying about clearing the cutoff, and you are actually thinking about kind of like is my rank single digit or something like that. Okay, so this is easy scoreable. If you can do well in this one subject, that makes a huge difference in the gate BMP5. Okay, most weighted, most important, most predictable. Top of that, this is easily scoreable. Scoreable. Okay, so to answers, notice I have already put up a set of practice questions on bioinstrumentation, practice questions. Okay, there are about 100 questions so far. Most of the questions that are showing up in the previous year question papers, gate question papers, are from these concepts. Okay, more than 95% of the questions are from concepts here. So this kind of covers very well whatever is required for the gate bioinstrumentation preparation. But on top of that, we'll also look at PYQs today. Okay, the point is, hey, you have all this nice set of questions, but looking at PYQs, you also get to know that you kind of get used to the gate way of framing questions, right? How does gate frame questions from a given concept, right? This is gate framing. That is something we certainly learn. Okay, and what I would ideally do is to first make sure I have understood the practice questions here, and I would be using the gate PYQs to test my knowledge. Okay, test and reinforce. That is what I would ideally be doing. And at that stage, as I said, your performance is like in the top 20 or something like that. Okay, fine. So today what we are going to do is to look at this bioinstrumentation question. This is part of the Simplified revision series. Okay, this is part of the Simplified revision series, right? We have already covered many subjects like, I suppose, circuits, HAP, biomech, and today we are planning to do bioinstrumentation. This is quite vast, so I will likely have to do two parts here. Okay, I have to do part 1 and 2. What we can do today in this video is this part 1. I have split that into two parts. Okay, otherwise it's hard to manage time. Okay, we can solve the questions, but we wouldn't have time to look at the basic underlying theory, bare minimum theory required to solve the PYQs. Of course, we are discussing solutions of the PYQs. This is kind of redundant. And by now, we have sufficient PYQs itself to actually find easy, medium, hard versions. Okay. So we have many questions where, say, most of them are moderate. Okay. There are also examples from many concepts, from the same concepts where we have easy version or hard version. Okay. There are many examples here. So I have arranged all these questions in a proper order as usual that I did for these topics. Okay. So we'll start from scratch. I suppose that is SCRATCH. Okay. We look at the bare minimal theory that we need. We learn it right now. Okay. And then we look at the solutions. That is one thing. So these questions, whatever I have here, are kind of sequence and a nice sequence, and these are also clustered. Okay, so let's head back to the syllabus over here. As I said already, the syllabus is quite vast. I have, let me read through it and then I will kind of simplify this. Okay, so we have sensors. Let's use kind of colors to highlight. 1 second. Just 1 second. Notice we have sensors. Basics on, what a resistor is, simple models for a resistor, and then capacitor, inductor. Okay, this is really, really basic. Most of you kind of know this. And then there are some specific sensors that play a very special role in bioinstrumentation and medical imaging. Okay, so that list includes PZT, okay, the Hall effect sensor, and then we also have this electrochemical and optical. Okay, so every year there is almost 2 to 3 questions just from this line. Okay, 2 to 3 questions. Then we have signal conditioning circuits that mostly kind of aligns with concepts from other subjects. There is a lot of intersection with electrical circuits, op-amps, and things like that. Okay, so this is one topic that in order to answer those questions, you need bare minimal circuits knowledge, if not some analog electronics and op-amp knowledge. Okay, so you need basic circuits knowledge for this. So let me deal with those questions separately. Okay, right now, yeah, there is also, notice this optical and laser. Typically there is one. Laser is used for sensing as well as for therapy. Okay, so I didn't underline it as a sensor, but typically from optical and laser there is one question. Okay, then comes the origin of biopotentials and measurements. These are most of the variables that we have, right? ECG, EEG variables, or even just measurement, devices. ECG, EEG, EMG, ERG, EOG, GSR, PCG. Typically, there is at least 2 questions from that. Okay, and then we have principles of measuring pressure, volume, and flow. There are typically 2 questions from cardiorespiratory measurements. In fact, if you add respiratory, that would likely become 3 questions. Okay, so this is adding the respiratory system, thus blood gas, lung volumes, and things like that. If you add that, there are about 3 questions every year. And then finally, we have some of this medical equipment. Okay, there is some basic theory question from this, 1 or 2 theory questions. And then notice some of the things mentioned here: cardiac pacemaker, defibrillator, and all that. Simple models for them are of the form of RC circuits. Okay, because of that, there are also many questions from here. Okay, so if I put this group together, again, every year there is almost, let's say, 2 to 3 questions. Okay, that makes it, notice. So when I say this is most weighted, most important, most predictable, easily scoreable, you have about, say, 2, 6, 9, approximately 10 to 12 questions from this. About 10 questions, okay? Let's make a bigger amount. Approximately 10 questions from this one topic. That corresponds to roughly, okay, anywhere from approximately 15 marks, okay, 15 plus marks, which is why I say this is one subject that can easily, help you clear the cutoff, or in fact, you can put up an excellent performance in the GATE biomedical paper by knowing this one subject in and out. Okay, and so today we are going to cover this. And notice, I already kind of clustered this, so there isn't a need for me, but I can be more specific on this. Okay, I have kind of made a small note on the type of questions that show up. Okay, so from sensors, first group is the RLC. Okay, there is typically a question from that. And then some of the important concepts here, almost every year, there is a question from strain gauge or Wheatstone bridge. I have it over here. Okay. There is a question from this RLC. Okay. Then there is a question from a thermal sensor. Almost every year there is a question from a strain or Wheatstone bridge. Okay. And then every year there is a question from one of the flow measurement techniques, typically Doppler, PZT, or Hall. Okay. So we have RLC, then temperature. Let me in fact write it over here as a shortcut. This is RLC. Then we have temperature, strain, and I'm going to club Wheatstone along with it. Okay, strain and Wheatstone, and then flow measurements. All right. So we have flow measurements. This is all from sensors. Typically, this is you could use a Doppler, PZT, ultrasound, PZT based question. Okay, both are kind of connected, Doppler or PZT. And then there is a question from Hall effect. This is from sensors. Next topic is cardiorespiratory. Okay. Here again, if I have to, okay, there is a question from pressure flow, blood flow kind of I already mentioned, blood gas, and then we also have lung volumes. Okay, lung volumes. So there is a question from measurement of pressure. Okay, this is measurement of pressure. Flow I already put. Volume. Okay, and then volumes include both, lung and heart. Okay, volume, lung, heart, circulatory system, lung and heart, lung and circulatory. That would be better word there. Lung and circulatory, and then blood gas. Okay, so there is a question from this. Notice I still haven't actually added ECG, EEG, and all that. That the common things that show up. So there is sensors 1, and there is also sensors 2. Let's write that. Okay, sensors 2. Here we typically have a question from origin of biopotentials, electrochemical sensors, membrane potential, and all that. Electrochemical, Nernst-Plant equation. Typically there is a question. Okay, and there is this optical devices, Snell's law, endoscope, question based on that. Endoscope, fiber optics. So all of them I have kind of clubbed together in opticals. Then one more thing, that question that shows up again and again is from opticals. Okay, because that appears quite often. I'm going to split that separately. This is Beer-Lambert. Of course, I didn't have time to write laser, but this is kind of already included somewhere else. And then we have variables. I'm calling them variables so that this is easily kind of recognizable. So in this list, we have this ECG almost every year, just one question from ECG. Okay. Then we have all this EEG, PCG, and things like that. There is a question from that, PCG, pulse oximeter. Okay. There is a separate question from that. And there is also this miscellaneous category, electrical safety, isolation, even some of the things in pulse oximeters and things like that. So in addition to this, we have this miscellaneous group, and there we have two types of things. Okay, questions that are really miscellaneous, that is like it's hard to club it in one of the groups that I have already discussed. And then this is one is Bioinst miscellaneous, and then we also have this combinations, signal conditioning circuits, basic RC approximations of defibrillator, pacemaker, things like that. Okay, so these are combination concepts that require some prior knowledge from other subjects. Okay, so this is a good way to cluster and group these questions. Okay, and again, this is almost every group that I have, color group that I have put in, there is almost 2 or 3 questions. Okay, having said that, what we are going to do today is we will do sensors 1. We will also do the cardiorespiratory system, questions from that. In the part 2, we will do sensors 2, some variables, and also miscellaneous questions. Okay, that is the agenda for today. And let's kind of make this really fast. Okay, all of you have a calculator, and if I am asking you to make the final calculation, please try to do it and get back with an answer as soon as possible. That is one thing. Also, theory questions, we'll try to not go deep, reasonably answer the question and move on. That's all what we want to do. So the first group is sensors 1. Okay. So this is this resistive, capacitive, inductive thing. Temperature, strain sensor, Wheatstone, Doppler, PCT, Hall. What I will do is I'll write down most of the formulas and things like that we need. Once we finish, perhaps we can come back and fill some of the formulas that we need here. Okay, we'll come back and do that, but let's get started. Which of the following sensors, displacement sensors, is known to have a high sensitivity and a relatively large measurement range? Okay, relatively large measurement range, that one requirement, this one requirement, right, kind of puts off strain gauges. Displacements are small. Okay, displacements are small. Even compared to capacitor, LVDT, capacitor displacements are actually small. Okay, on top of that, you say this is highly sensitive. That makes this differential transducer, linear variable differential transducer using inductors as the answer. Okay, just by that relatively large measurements kind of ruled out most of the options. Okay, when it comes to sensitivity, certainly even this kind of gets ruled out. Capacitive sensor gets ruled out. What these are, we'll not get into that. Could quickly Google, but as I said, strain, piezo, and all that displacement cannot be very high. Let's move on. Okay, two inductors with details given below or wound separately. Two inductors with the details below. 1 second. Yeah, two inductors with the details given below or wound separately on two identical ring-type ferromagnetic cores. The ratio of the two inductances, self-inductances, L2 and L1. Parameters given are the number of turns, the gauge of wire or the thickness of the wire, which to make the inductor. Right? So we will have to presume a cylindrical core. The shape is not given, but we presume this is cylindrical inductor. And based on that, notice the inductance for that is mu A N square, right? I kind of have a sort of a mnemonic. So this is mu N square by L. Typically, sometimes there is a correction factor, okay? But mu A N square by L is the inductance, self-inductance, okay? So given that the gauge doesn't matter, thickness of the wire doesn't show up. So if we have an inductor, right, we have this cross-sectional area, typically this cross-sectional area A, a length N, length of this coil, and then we have the number of turns. We have, let's say, 1, 2, ... till N. That matters. The thickness of this wire doesn't matter here, okay, for inductance. So given that the ratio of these two inductance, the gauge doesn't matter really. So this parameter is immaterial. This is where they are trying to give you the extraneous information. So expecting you to know, if you really don't know what the inductance is, hey, let me do some kind of use gauge. They have given gauge of wire, let me use it, right? Some means. And they are expecting you to do some kind of amateur mistake like this. But I suppose you recognize this is immaterial. It only depends on the number of turns. In fact, depends on the square of the number of turns. So this ratio is going to be L2 is proportional to 2n square. L1 is proportional to n square. If other things are not changed, this is, and to avoid any confusion, what I have written here is this length L, okay, length of the coil. Okay, so this becomes 4. Yeah, great. Let's move on to, so basically you should be able to calculate resistance, capacitance, inductance, those three things. And typically inductance, you need to know it for at least for a cylindrical core. Let's go to the next one. Which of the following temperature sensors is used in contact type digital thermometers for measuring body temperature? This is contact type. The first thing that I'm trying to do is to certainly rule out incorrect options. Okay. So we know that infrared LED photo detector pair. Probably this is, infrared is at least used in non-contact type, but the given description seems to be both, this is, sounds like pulse oximeter. But worst case scenario, okay, non-contact, you need infrared, right? You need this kind of setup in pulse oximeter and non-contact type, non-contact. Rest of the things you need a contact. You have to put the thermometer in your mouth or something like that, right? Mouth typically the mouth, sometimes the ankle, and all that, depending on the context. But notice it has to meet certain criteria. One is it has to be sensitive and specific in the range of interest, in and around body temperature. Okay, around 37 degrees Celsius. This is where it's working. Okay, and then this has to be reliable, robust, shouldn't easily get perturbed by many things, and cost effective. Given this, the thing that best stands out here is a thermistor. In fact, there isn't any industrially provided thermometer that kind of uses for biomedical purposes, that kind of uses either a thermocouple or a RTD. Okay, they kind of in fact, there's one detail. This has to be sensitive and specific around the 37 degrees Celsius, right? The working range is kind of very, very narrow. And the thing that works best in that narrow range, it has to be highly specific plus cost effective. This is a thermistor. Okay, this is a very narrow range, and thermistor works best there. Great. So most of you know this. That's good. This is a narrow range, right? That is where we want this to go. That makes the answer B. Again, most of you know this. So at this stage, you need to know what a thermocouple is. Where is it used? Probably a heat bag or a heating seat, heating cooling seat, heating gel, cooling gel, something like that. A thermocouple is likely to be used, right? So again, RTD is not in biomedical applications typically. Okay, go for a thermistor. Another thing that you want to know is you are also expected to know simple models for this, that is mathematical relations for this. Let me show you some examples on that. Example PUQs on that. Simple models for this. Okay. For example, I suppose the first thing is RTD is not there in most biomedical applications, but it's a temperature sensor, right? What are some simple ways to model that, right? A linear temperature coefficient. This is of a material of, linear temperature coefficient of the material of a wire is some unknown x into 10 power minus 4 per degree Celsius. Resistance of this wire increased from 50 ohm at 25 degrees Celsius to 60 ohm at 75 degrees Celsius. The value of x is. Okay. It's a very, very simple question. This is a question from RTD, but that year most of the students got this incorrect. Okay. Simple question from RTD. What most of the students did is they read this. So you have resistance at a particular temperature is resistance at some other temperature into 1 plus alpha delta T. This is what most of the students did. Okay. In the process, what they wrote down as, let's say, resistance at temperature 25, 75, this is 60. Okay. At 25, this is 50. 1 plus alpha, and the delta T happens to be 75 minus 25. That is 50. So this is in degrees Celsius. So alpha into 50 right now is dimensionless. So alpha automatically is in degrees Celsius. If you find alpha from this, can you quickly tell me what is the value of alpha? But while some of you are calculating that, let me tell you right away, this is incorrect. This is what most of the students did. They didn't score it. Just try it out. Okay. But what you're supposed to do is this, known as, by definition, linear temperature coefficient is defined with respect to alpha. Let's call it alpha is defined with respect to 0 degrees Celsius. I suppose, okay, someone found the answer here. They are saying this is 4 e power minus 3. So in terms of writing it as x into 10 power minus 4, I suppose I'm getting 40 into 10 power minus 4. Degrees Celsius inverse. Okay, but that's incorrect. Notice alpha is defined with respect to 0 degrees Celsius. What that means is resistance any temperature depends on resistance at 0 degrees Celsius into 1 plus alpha temperature of interest. Okay, notice based on this, what this says is you have at 75 degrees Celsius, you have 60. So there is let's say R0, we don't know what R0 is, that is resistance is 0. So we have alpha into 75. Okay. And then at temperature is 25. Okay. We have resistance to be 50. Again, we don't know what R0 is, but if you divide these two equations, I get this R0 will get cancelled. Right. what we have here is 60 by 50 equals 1 plus alpha into 75 by 1 plus alpha into 25. Alpha is the only unknown. You should be able to solve for it. And can someone quickly solve for that and tell me alpha? This is just a linear equation, right? This is 60 plus alpha into 60 into 25 equals 50 plus alpha into 50 into 75. That's fairly straightforward to solve alpha. Just do that and let me know what alpha you get. Yeah, if you do it this way, the alpha that you get, the correct alpha that you get is, you should get 4.4 into 10 power minus 3 into 10 power minus 3, right? Sometimes we write this as 4.4 e minus 3. Okay, this is notation, engineering scientific notation. And if you write it in powers of 10 power minus 4, this happens to be 44. Again, there are like, I suppose there's 4444, right? So 44.4 into 10 power minus 4. That makes your answer. Let's write that out very clearly. 44.44. Okay. I'm not writing some 4s over here. 4444. Okay. This is 44. X is that. So be careful about this detail, because this is just a conventional detail. Alpha is defined that way because of this. Notice this almost looks the same, right? Because of that one certain detail, almost everyone kind of lost marks after the exam. In hindsight, right, we kind of, okay, this is convention, is set this way. Okay, at least now we should acknowledge. Okay, let's move to the next question. Yeah, this is a mathematical model for thermistor. Okay, so thermistor, this isn't about any specific temperature. Unlike a RTD, this is like, give me resistance at 2 temperatures. Okay, this axis is temperature, this axis is resistance. Give me 2 temperatures A and B. I can relate the resistances in those 2 temperatures, right? There is an exponential relation. Typically, this is a coefficient is negative, so this looks like a drop. Okay, this is resistance is decreasing with temperature. Okay, that is one thing. So tell me the temperature, I can relate this fairly easily. So tell me this point, this is, let's say, RA. Okay, and let's call this point B, and let's say this is RB. RA and RB are related. Quick mnemonic that I use for this is AABB. So we have resistance at temperature A equals resistance at temperature B, okay, into e power minus 1 by temperature of A minus 1 by temperature of B. Let me say what I meant by this mnemonic, because sometimes this order is easily confused. Okay, so I have RB, TB here. RB, I'm writing this in a different order. So I'm supposed to have TB here. TB and then TA. Okay, and this minus, this is this minus. Let's quickly make sure, the relation that I have written is correct. Else we'll go change the mnemonic. Okay, we need to somehow remember this, right? I suppose the mnemonic is right. Can we confirm if this is correct? So given resistances at any 2 temperatures, you can easily relate the, and suppose, yeah, this is correct. That's why, mnemonics kind of make your life easy. What they are asking for is this temperature coefficient beta. Hey, this is typically the decay rate changes. So obviously there is a minus beta there. Okay. What they are asking for is, what is this value of this beta? Different materials, the decay can have different rates. Beta determines. Okay, so given this, let's write on, we are given this, right? We have the units, actually units of RA, RB and all that will get cancelled. Kilo, yeah, notice, let's say RA is 1000 ohms. RB, let's kind of write it in that format itself. Okay, so we have 1000, that is RA. RB happens to be 500 into e power minus beta, that is what we are trying to find. We have 1 by TB. TB is 50 and then TA is 25. Beta has units of degree Celsius inverse. So where is this units going on? Find the temperature coefficient of resistance in units of degree Celsius inverse. I suspect a typo there in the gate question, but let's go ahead and find beta and then answer. The beta is the only unknown. How do you go from beta is somewhere in the power, remove the power, How do you undo the power? How do you undo the power? Take ln on both sides. It's a very standard trick by now. Okay, ln on both sides, ln function, not LAW and ln. This is ln function on both sides. The beta will come to the ground and we can find what the beta is. Just tell me what beta is, and meanwhile I'll clarify if there is a typo there. This is 1 by t. This makes or beta. What I did for beta. Okay, so what they are asking for is not beta. What they are asking for is sensitivity of this. Okay, so some of you, thanks for doing this calculation. I suppose the answer is not 34.5. Okay, so there is something called sensitivity of this that has units of degree Celsius inverse. Okay, right now notice this beta is as most of you are saying this is 34.5. Beta needs to be in degree Celsius. They are asking for something in degree Celsius inverse. One of the parameters that is there is this is known as sensitivity. Okay, let me write it over here. Sensitivity. Okay, this is by definition 1 by r dr by dt. Okay, this is the slope of this curve, normalized slope of this curve. Notice this has units of resistance unit gets cancelled. This has units of degree Celsius inverse. Okay, and for this given relation you can take the derivative and you can quickly calculate this to be minus beta by t square. Okay, beta is in degree Celsius, temperature is in degree Celsius square, so you'll get degree Celsius inverse. Okay, I suppose they are asking for the sensitivity. Let's just calculate that. Sensitivity. Okay, this happens to be minus beta, and yeah, this actually sensitivity. There are actually strong giveaways there. They are asking for coefficient at a particular degree Celsius. Okay, this beta is independent of temperature. That's the point of that constant. But what they are asking for is at a specific temperature, 35 degrees Celsius. So they are indeed at this stage, I would say, referring to the sensitivity. If you calculate that, so beta is 34.5 divided by 35 square, I get 0.28. 0.028. Can someone also check the key for this? Answer key for this. And we can also do that. GATE 2023. Question number 55. Okay, supposed to get sensitivity. This is minus 0.00, or sensitivity is minus 0.028. Okay, the given answer key is minus 0.03 to minus 0.025. So I suppose they are asking for this sensitivity. Okay, I kind of actually want the plan that I had is find beta, answer it, and then go say there is this one more important parameter, sensitivity, that they typically ask. I was about to say that, and then when we find beta, I kind of recognize, hey, there is a issue with the units. This finding sensitivity, of course, seems to be the thing. Okay, and then the question is, hey, is this temperature coefficient of resistance or is this sensitivity of the thermistor, right? That becomes a question of convention. Okay, which book you are referring to. Okay, a smart thing would be to actually just go by the units that I mentioned. Okay, I got how should I put it? I got saved by the units because I was cautious about what they are asking and what they were finding. So at least that should happen. And there aren't many other things. There is just this beta and then the rest is sensitivity. Okay, so notice there is also this negative sign here because the thing is always dropping, right? This slope is negative, and that is kind of showing up in the sensitivity. Okay, so again, most of the things that you need to know for a thermistor, it is here. And typically, there is a question from either a RTD or a thermistor, both of which can be easily monon. They have a mnemonic for help, and then this derivation is like 1 or 2 lines. You could try doing that. Just use this relation. Most of the terms will repeat. And this, the beta will get multiplied. You will easily get this term. Okay, let's move on to the next one. Metallic strain gauge. Okay, so thermal basic temperature based questions, right? We have basic theory questions. The numericals either from a RTD or from a thermistor. Now let's go back to a PZT. Yes, metallic strain gauge with negligible piezo-resistive effect is subjected to a strain of 50 microns. Actually, it's not. So dimensionless. They're 50 10 power minus 6. For the metal, Young's modulus is this, Poisson's ratio is this. What is the change in resistance if the unstrained resistance of the strain gauge is 200 ohms? Regarding strain gauges, you need to know two things, okay? Let's look at the basic relations and then we'll come back to this. Strain gauges. One is, there is something called gauge factor that can be found from Poisson's ratio, okay? Second is, where is this gauge factor? No, the way to derive this gauge factor, use resistances rho L over A, take ln on both sides, okay? Find this relative change in resistance, normalized change in resistance, relate all of them, and notice these two relative changes could be related using Poisson's ratio, okay? That is how it shows up, and then the gauge factor will show up there. And the end result will be this. The end result is typically when there isn't any change in resistivity, when there isn't any change in rho, your normalized change in resistance, it's proportional to the normalized change in length. Notice the normalized change in length is what we refer to as the strain. The proportionality constant will happen to be the gauge factor, is one thing. Do I have hacker? Yeah, okay. This is one relation. And the third important thing that you need to know was, typically the strain gauges are put in a Wheatstone bridge. There, the output voltage again can be written in terms of the gauge factor. This is output voltage. This is proportional to the input voltage. It depends on G epsilon. Again, the same thing. Okay. But we have correction factors here. Depending on the type of Wheatstone bridge, we'll have to do that. Now, I'll perhaps come to this one particular detail in a minute. Right now, let's put a N by 4. So what are the things that are all related? Gauge factor, Poisson's ratio, strain, normalized change in resistance, del R by R. Okay. What they are given there is metallic strain gauge, I suppose. Strain is given. Let's just list down what is given. Okay. Strain is given, epsilon. Young's modulus is given. Let's write it. Okay. E. Poisson's ratio is given, nu. What is the change in resistance? Del R. If the unstrained resistance is given, they are asking for this given the rest. I suppose they are given this. They are asking for del R. At this stage, we can easily write down what is del R. There is this one relation, right? You have del R, normalized change in resistance, equals gauge factor into strain. And gauge factor, I just mentioned, can be found using Poisson's ratio, right? This can be found using Poisson's ratio. Specifically, that is 1 plus 2 nu into epsilon. Okay. So, yeah, here, in fact, notice this is again one more extraneous thing that they have given. Okay. If some other information is given, okay, stress or something is like that is given to find strain, then Young's modulus is required. But strain is directly given. In the case you don't need Young's modulus, this is given as a distraction. Again, some numbers are given. Let's multiply, divide. Let's try to find the NAT answer, right? Guess kind of set for those students. Okay. So right now we know R, Poisson's ratio, we know strain. Can we calculate del R? They want the change in resistance, right? And let's find del R in milliohms. Okay. Do everything in SI. Typically there will be a 10 power minus 2 or minus 4 slightly converted into 10 power minus 3. Okay. Del R is dash milliohm. Okay, I have to kind of shift gears quickly. Hopefully, one of the theory questions can. Okay, great. So when you calculate this, I suppose you are getting 18.4 into 10 power minus 3 ohm. Either you are getting this, or let's say you are getting 1.84 into 10 power minus 2. This is likely what you are supposed to get. Okay. Just put one more, change the decimal and write it as 18.4 10 power minus 3. And that becomes the answer as 18.4 million. See, if strain is not given, you need Young's modulus and stress. Is there an example like that? No. This is the third relation that I have. Then, yeah, if stress is given or something like that, notice there is a question here where that kind of extension shows up. Okay. Notice here in our example right now, if they had not given strain, you need both stress and Young's modulus to find it. If this strain is not given, right, Then you need some other information to find it. That information would be sigma and E, right? You need stress and E to find it, because we also know that sigma is E epsilon, right? We have done this biomechanics, biomaterials and all that. Great. Yeah. Now let's look at this question. We have a Wheatstone bridge arrangement of those resistors, strain gauges essentially, okay? Arrangement of 4 resistors in a diaphragm for physiological pressure measurement. If this isn't clear, let me read it, okay? Arrangement of 4 resistors of equal value in the diaphragm of a physiological pressure measurement catheter is shown below. Applied pressure is observed to cause an increase in length of resistors, R2 or 4. That detail is important. Let me underline that. And an increase in cross-sectional area in R1 and R3. At this stage, I know they are referring to R2 and R4 are in tension. Its length is changing. R1 and R3 cross-sectional area is increasing. I know they are in compression. Okay. The operation results in an equal change in values of all 4 resistors. So equal change, but sign should be opposite. Okay. If tension resistance changes del R, compression resistance change should be minus del R. Value is same, but signs are different. Which among the configuration given below should be used to connect the resistors to form a Wheatstone bridge, so that the bridge output is proportional to the change in resistance of individual resistors? Fine. You need a bridge output voltage. What you really need is an unbalanced bridge. And identifying unbalanced bridges is fairly easy. Okay. Requirement for unbalanced bridge is fairly easy. You know the balance condition that should be violated. Unbalanced bridge. So what I'm going to do is to draw these. Okay, let's R1 and R4 tension. Let's give it a different color. Rang de basanti, right? So this is okay, compression. Let's put it in red. Quickly, you have this is in tension. This is in tension. Cross-sectional area is given. Lateral strain is increasing. So longitudinal strain is negative. This is in compression. This is in compression. How about the option 2? This is in tension. This is in tension. This is in compression. This is in compression. At that stage, notice, even if the resistance has changed, if they change by equal amount, this is balanced. You won't get any output here. This, on the other hand, is unbalanced. Unbalanced. And typically that arises if we have this similar changes in diagonally opposite sides. If you have them on the same side, a bridge remains balanced, okay? So because of that, you only have option 1 where it is possible to measure. Option 1 only is unbalanced, only that can show an output voltage. Which brings us, notice, now in this bridge we are using 4 resistors, but that's not always the case. I have answered this question. I'm just going to, I left a blank over there. Let me quickly answer that. Hey, notice, strain gauges, every year there is a question, okay? Strain gauges, 2023 there is a question, RTD, right? Now 2020 there is a question, and 2023 there is one more question, 2022 there is a question. Almost every year there is a question, okay? And you could also add a Wheatstone bridge. If you consider that, there can be AC Wheatstone bridges also. So typically there is a question, there is always a question from AC bridge, right? But for that you need to know impedance. But right now, notice you have this, I have space here, but I can draw it here itself. What is this N? N depends on the type of bridge it is. That is the number of resistors change you are making use of. Okay. Number of resistance change you are making use of. Okay. So let's draw that. Bridge 1. Let's kind of draw it here itself. Okay. Bridge 1. Bridge 2. There is an input. There is an input. There is an input. And we measure the output at the other ends. Technically, there are 4 resistances. Resistance 1, resistance. There are 4 resistances in each of the individual, edges here. Out of the 4 resistances, not all of them need to be functional. Okay. Like in the scenario 1, in this one, actually, let's say if you were to mark this, right? If you were to write situation 1 here, what is given as, hey, this resistance is changing, this resistance is changing, and then this resistance is changing, and this resistance is charged. All 4 are made use of. Sometimes only 1 is made use of. Okay. Sometimes 2 are made use of. The other 2 kind of are there. Their resistance are not changing. Only there is a del R here, del R. Okay. Other resistance are not changing. Del R, and notice this is minus del R and minus del R. For imbalance, they are diagonally opposite. Similar ones are diagonally opposite. Okay. And this is referred to as quarter. You're only using 1/4 of resistances. Half full. Quarter half full what? quarter half full Wheatstone bridges. Okay. So this N that I wrote here, notice input voltage, output voltage is kind of over here. Input voltage, your input voltage, let's say you are applying here. Let's use one more color. Input voltage, input voltage, input voltage. Your output voltage, you're reading, of course, of the green. Okay. You're between these two edges, between this and this, you're reading V out. Okay. V out, V out. So output depends on the input. Again, this is G epsilon, but there is a factor of N by 4. Okay, now let's elaborate what that N by 4 is. Let's again give it colors. This is N by 4, okay, N by 4, and the value of N and the type of bridge that we have. N is 1, 2, 4, not surprisingly for a quarter, half, full. In other words, output is the highest when sensitivity is the highest, output is the highest when you are using all resistance ranges. Full bridge. 4 by 4, that is 1. Half bridge, output voltage is only half. Okay, half of the full bridge. Quarter bridge, N is 1, so 1/4 of the full bridge voltage output. Okay, so this is it. So this is, this you need to know type of the bridge. For example, based on the configuration here, notice what they are referring to is this bridge 1 as a full bridge. Bridge 2 is not functional. Okay, bridge 1 is full bridge. Okay, and this is this bridge 1 that they have given an option. You can recognize from either from the description or from the diagram. And notice this part G epsilon can be substituted with del R by R. G epsilon is del R by R, normalized change in resistance. Okay, or epsilon can be given in terms of sigma and sigma and D. Sigma and D are known epsilons. G is not shear modulus. G is gauge factor. Okay, I kind of wrote it down because there is Young's modulus. A is a shear modulus now. Because given Young's modulus, given Poisson's ratio, you can find shear modulus, you can find bulk modulus and all that. Let's not confuse it with that. This is slightly different. Example PYQ. I think we have a PYQ, right? Let's look at this. Wheatstone bridge. Gauge transducer is constructed on a diaphragm such a way that when a force is applied on the diaphragm, resistors R1 R4 will be in compression. Here they are explicit, right? R1 and R4. This is in compression. This is in compression. Then these two are in tension. Here they are not mentioned positive negative terminals. So I am also like, I am not, these two are different colors, different signs. That much I know. So I just said your V0, this is V in. What kind of a bridge is this? This is full bridge. Full bridge. Let's emphasize that. We have a full bridge. Okay. So you have 4 by 4 into G epsilon. G epsilon is given. No, that is not the change in resistance, and resistance is given. So of course you can write this as, notice, 4 by 4 into del R by R into VI. I suppose all of these are given. You could find what the output voltage is. Del R is given, R is given, VI is given. Can we quickly find out what the answer is? We have del R to be 20 ohm, R to be 200 ohm, input voltage, excitation voltage to be 10 volts. I need a piece of cloth. Actually, my fingers are kind of scratching the tablet, Wacom tablet, and irritating. Trying to find a piece of cloth, but it's not there. But yeah, for no, it's my pinky is only getting targeted, and it's somewhat very irritating. That is why I'm like kind of course my hip is also, there's a mild pain, but this finger is irritating. Okay, yeah, this is technically, this is 1. Okay, technically they haven't given what the polarity is, so ideally both plus or minus 1 should be okay. Okay, E in, which is positive, negative there, that is not mentioned, so either should work. Okay, plus or minus 1. You could go verify what the key is, I don't know, but I know that. Right now, let's move on. Catheter based arterial blood pressure measurement device uses a flexible diaphragm mounted with 4 identical strain gauges and a Wheatstone bridge configuration as shown. Okay, there are 4. This is again full bridge. Right now, I recognize this to be full bridge. Assume that the strain gauges have a nominal resistance. RG, starting resistance is given, gauge factor is given, Young's modulus is given, blood pressure variations result in small finite change in strain. What is, if V0 output voltage, V0 is the output voltage, sigma is a stress MPa, presumably in the strain gauge, the sensitivity, V0 by sigma. Here they don't explicitly measure stress in what? Stress is in the artery, is it? Stress in the catheter, is it? Not explicitly mentioned, but of course, this much amount of common sense they expect you. They are referring to the stress in the strain gauge. Okay. Longitudinal stress in the strain gauge. So that is fairly known. What is our relation? By now, this is fairly simple, right? V naught is 4 by 4, okay? This is full, so that I'm writing it as 4 by 4. G epsilon Vi. What is given here? Vi is given 2 volts. This is Vi is given. This is given. Gauge factor is given. This 4 and 4 get cancelled. They are asking you V naught by sigma. Of course, right now, Young's modulus is also given, I suppose. Yeah, Young's modulus is given, notice. So that tells me a right strain as stress by modulus, right? So at this stage, I'm writing this is G into sigma by E into Vi. Notice this is dimensionless, 1 plus Poisson's ratio, no dimensions. Sigma and E have same dimensions, dimensionless. V, so left hand side, right hand side has units of voltage. Okay. So if what they want us rather, V naught by sigma, that should be G Vi by E. Keep this in volt, keep this in MPa, you'll automatically, or rather I should put it this way. Okay. Keep this in volt, keep this in MPa, you'll automatically get the answer in the required unit, that is volt per MPa. Fairly easy. I suppose most of you calculated. Thank you. That is okay. That's your answer. Fine. So notice most of the things that you need to know is over here. And let's actually declutter them. And on this go anyway. This is a starting relation using which you get the gauge factor. You study the sensitivity of changes here, automatically you get gauge factor. And then del rho has to be 0. That is one thing. And then you have sigma is 2. Fine. That brings us to the next topic, I suppose. Flow probes. Great. An 830 nanometer Doppler flow probe is oriented at angle 60 degree to the flow axis. Average flow velocity is this. Magnitude of the Doppler shift frequency is. Again, almost every year there's a question on this, okay? Doppler flow, what is a Doppler shift? Notice here they're asking you for this Doppler transducer is made using PZT. So there is a question on PZT. Look at this next question. Doppler shift. What is a Doppler shift? Again, there is a question on that. What is this? Oh, this is a different type of flow meter. There is a C-clamp flow. But anyways, we'll come back to this. Let's go back to that question. So what do we need to know here? Doppler shift depends on the transducer frequency. Frequency is frequency. Right now, dimensions. 2 cos theta U by C. 2U cos theta by C into F. Okay. I wrote it in a way such that the dimensions and all that. That is, I recall that. And I have written it in a way such that the dimensions and units are clear. You have a blood velocity, there is an average blood flow velocity U there. And you have the probe at an angle theta to that. Okay. You have the probe at an angle theta to that. And then there is this probe frequency F. Okay. Because the blood is moving, you can shift between transmitted and received signals. That shift is referred to as this Doppler shift of the transducer. Let's say the transducer somewhere here. And what is the C? C, we have to be careful. C is the speed of whatever it is. If this is a laser probe, so this is the speed of that light, speed of the method. Be careful. Yeah, which is what just because it's Doppler doesn't mean it's speed of sound. Doppler shift occurs with light. Any wave Doppler shift occurs. Yeah, any wave Doppler shift occurs. What I was quickly thinking is relative changes in velocity doesn't happen with light. Okay, speed of light is a constant. Frequency of light will change. Okay, so Doppler shift, be it a sound wave or a light wave, does happen. This is the speed of the method. If it is light, it is light speed. If it is sound, it's sound speed. And if it is sound in air, it is sound in air. If it is sound in tissues, speed in tissue. Sound in blood, speed in blood. These are slightly different. Okay, be careful. So laser, this says that's important. C is 3 into 10 power 5 meter per second. Sometimes, in fact, some of these terms gets cancelled. Let's see. So what we need is this del F. This happens to be 2. Angle is given to be cos 60 degrees. Okay. Nanometers. Wavelength is given. C by F, I suppose, is wavelengths, right? U, this is lambda F into F. In fact, F will get cancelled, right? In fact, you don't need to know that F because this will get cancelled. And in this case, get it in hertz. Hertz is SI. Then get that 10 power 3 in front of that. Okay. So this is 2 cos 60 degrees into U. Right now, 3 into 10 power minus 2 centimeters. I'm substituting everything in SN. Finally, I'll convert, when I am entering, I'll convert it to the required answer. This is 830 into 10 power minus 9. This is in meters. Sorry, this is in hertz. I should get the, already I explained the dimensions. This should be per second, that is hertz. Tell me, the final answer in kilohertz.
Step of this one. What is there? Okay, this shift is here. And then I have the flow measurements, isn't it?
Yeah.
What did he promise me to do today?
Is it sensors 1 and cardiorespiratory? Yeah, let's do it. Okay. If we get the answer, is an issue going to concept 10 formulas to divided by 830 divided by 10 power minus 9. I get 36144, that is 36.14 kilohertz. Okay, that was 36.144. I got 36,144 hertz in SI. In kilohertz, 36. Okay, now the question. Okay, this is not light, laser. What determines that laser frequency? In case of PZT quartz crystal, what determines that frequency of the transducer? Right? So this is where, there is this, the way this standing waves, resonance happens, right? You get multiples of n by 2. This wave is possible in a resonating, 1D resonating medium. Then you have multiples of that, right? These resonances are kind of possible. The starting one is this, where the length is kind of a place for laser as well as for PZT crystal thickness. The thickness of the resonating column is half the wavelength, the starting wavelength. So this is where we get this. Your D is lambda by 2. Requirement for a standing wave or resonance. Okay? 2n by 2, 3n by 2 are also there, but what really dominates is the first mode. So given thickness and this wavelength are related, of course, you can write this as C by 2. Yeah. Lambda is C by F. Right? What is given as F is given, C is given. Notice velocity of sound in the PCT crystal, because we are now the transducer itself, we are kind of discussing. This wave is within the transducer. Then it comes out. But that standing wave resonance is happening within the transducer. Okay? Great. So now, again, the C is given, F is given. Put it in SI. Finally, write it in. You'll get the answer in mm. Sorry. Substitute everything in SI. You'll get the answer in meters. Write that in mm. Okay? C is 4350, okay, meter per second. Then F is 510 per hertz. SI for frequency is hertz per second. Okay? Substitute that. You should get to work at a resonance rate, you will get the thickness. Okay? So this is the condition for resonance. Fairly easy to calculate. This is 4530 divided by 5 divided by 10 power 6. I got 90.6 in, I should also divide by 2. Yeah, what I'm getting is 4.53 into 10 power minus 4. This is, let's be careful. If I donate 10 power minus 1 there, and this becomes 0.458. Yeah, math. Right now, this was in meters, SI meters. That's the answer. What have we see? Shift us to U cos theta, U by CF. Okay. Now, that F, they want to complicate it, can be given based on thickness of the PZT. They have already done one such complication. A crystal of thickness 1 mm and wave velocity 4000 meter per second is emitting a longitudinal pressure wave, which is incident on a blood vessel at an angle of 30 degrees. Doppler shift in, what is a Doppler shift? Blood flow velocity is given, wave velocity in the soft tissue is given. Propagation velocity is there, and the transducer velocity is there. You have to use appropriate velocity appropriately. Let me make this more explicit. The same form now. Del F is 2 cos theta, U by C F. F is not given. You have to find F from something else. So I'm going to write C. F has to be inferred from notice. This is not laser. In this problem, when I did this happened to be laser. And you see its light speed, lambda F and F gets cancelled. Okay? But this problem, you have to be careful. We cannot cancel this We cannot write this as lambda f, and we cannot cancel that. Reason being, the speed is different. The speed is the sound velocity in soft tissue. Okay, the actual CF is different, so you cannot make this cancellation. Be careful about it. Okay, so let me write this as right now. This is C tissue, wherever you are imaging, right? C tissue, and this F. Let's also give it some color. That F should come from the thickness, right? So notice. So you have lambda by 2 is D. Okay, that lambda is essentially C by 2F. And here, this P, you have to use a wave velocity in the crystal thickness. PZT wave velocity. PZT. Okay. Those two speeds are different, so you cannot blindly cancel those two things. So I suppose thickness is given, the speed is given. This is CPZT. Okay. And then what you have here is C tissue. Yeah, now you can find, you have to put this frequency over there. That is fine. If you have to write this is 2 cos theta u by C tissue. Okay, that into frequency will be CPZT by 2D. Substitute everything in SI, you'll get the answer in SI. Okay, let me also do that. This is supplementary. What I have here is 2 into cos theta is given to be 30 degrees. Okay, into u velocity of blood, that is 10 into 10 power minus 2. Okay, into CPZT, that is 4000. C tissue, that is 1540 by 2 into D is 1 mm, 10 power minus. In fact, let's write it as 1 into 10 power minus. Everything is in SI. I should get the answer in SI. Okay, answer when I calculate this, I should be in SI, which is also happens to be the required given. How do we get here? Yeah, 225. I remember the answer K was something like that. Okay, fact, this is 2. And look at the way that I am dealing with units. Okay, SI finally when I enter a converter, L units is a big mess. And gate calculator have sufficient precision. Okay, don't think about losing precision on all that. Okay, what we have here is this C clamp probe meter. I have the C clamp. Okay, this is typically, in fact, sometimes it's actually even like this. Okay, so that this is typically you can open this up somewhere slightly so that you can put it around an artery. So typically this is done invasively. The artery needs to be exposed. Okay, this is the artery wall. What is inside is a lumen. This is how the C clamp flow probe, and there typically you have 2 sensors. You have the electrodes, and you can apply a magnetic field in the perpendicular direction. Have a B field, and you can measure voltage. This voltage that you measure is just BLV. It means L. L is, see, the length of the moving conductor between the electrodes. This happens to be the length. The diameter happens to be the length. Okay, in this case. Into V, velocity is perpendicular. Oh my god, I am running out of colors. Velocity is perpendicular. Notice E, B, and velocity are perpendicular. Okay, the conductor is moving perpendicular to E and B. So it kind of, in applied magnetic field, there is a voltage generated. This is Hall effect used in C clamp or flow probe or C clamp magnetic flow probe, C clamp meter. Okay, and this velocity of the flowing blood is V, average mean velocity again. So if you want to account for the fact that this is average, you can have a correction factor here, but is typically 1. Okay, so your epsilon is BLV. What is given here? Let's look at it. What they want is the flow rate. At this stage, I'm going to make a small correction here or small modification. This is BLQ over A. Okay, what is what? This is the measured voltage. We don't want confusion between velocity and voltage. That's why I write it as this sort of big epsilon or E. Okay, voltage. This is a magnetic field, magnetic flux density. This is in Weber per meter square. Weber is SI, fortunately. Okay, magnetic field strength, and then you have the length of the conductor the C clamp probe meter, this is always a diameter. And this happens to be the velocity. This term is velocity. Velocity of blood. Blood acts as the conductor that is flowing here. Okay. So yeah, this velocity, mean velocity as flow rate by cross-section area. This is something that we have seen in fluid biofluids. Okay. Simple relation here. Flow rate is velocity into cross-section area. Volume per unit time. Notice this as units of meter cube per second. This is units of meter cube per second. SI units. Okay. So this is Q over A. You can slightly rewrite this D. Now, in terms of L is D, let me write it at the diameter D. Okay. L is the length of the conductor. That is the diameter D, Q by 4 pi D square into 4. Okay. Pi R square, that is pi by 4 into D square. That's what, that is the area that I have. So most of this is given. B is, fortunately, Weber is SI. Okay. Diameter, inner diameter of the clamp, this is given. Okay. This technically almost, the precision, this is almost touching, the clamp is touching the artery. There is no gap. So that happens to be that. Okay. And diameter is given. And then even the voltage generated is given. This is given. And you have to find what is this flow rate. Okay. Hey, can someone, it's hard, this calculation is slightly involved. You may not get it in a minute or so. Let me not wait. Okay. I have more questions. But I have done this in gateway discussion. Or why not, let's do it. Give the answer. And so this equals, I have a relay state issue. I'm running out of space. Fine. Give me an answer in, get it in SI, then meter cube per second. Conversion to centimeter cube per minute. Oh, this is centimeter cube per second. Okay. Just put everything in SI. Just tell me this in meter cube per second. Okay. We'll enter the answer in centimeter cube. I thought it's centimeter, liter per minute or something. For the centimeter cube, that conversion is fairly easy. So Q, everything else is known, only Q is not known. Okay. Let me write voltage is 3.75 into 10 power minus 9. Okay. Into pi, I'm approximate that by 3.14 into D square. Okay. 0.5 square into 10 power minus 4. Because it's in centimeters. Divided by D. Actually, 1D will get cancelled. Fine. Worry about it. I'll cancel it during calculation. B is 1.5 into 10 power minus 5 divided by D. That is 0.5 divided by 10 power minus 2. Okay. Divided by 4. Hopefully someone save me with the correct answer. What I am getting is 9.8 into 10 power minus 7. So 10 power minus 6 will be swallowed by the centimeter cube. This is in meter cube. So centimeter will swallow 10 power minus 6. What I'm getting is 0.98. Is it right? I am getting that. I know best to check the answer. 0.18. What I got here is 9.8 into 10 power minus 7 meter cube per second. If you swallow 10 power minus 6. Yeah. That is 0.9. Okay, now let's move on to this. One more flow question, Hall flow. Hey, there is a typical thing, right? The moment you can easily cook up what I refer to as a 2-scenario question. One question is, hey, given any 3, you can find the other. That type of question I have again and again discussed. Right? One more typical question that shows up is this thing called the 2-scenario question. Typically, A1 is A equals BC. Some kind of relation is there. In situation 1, B is 10% higher, C is 50% lesser, something like that, they will cook up. Normally it is this. In situation 2, okay, normally let's say situation 1, this is whole square. Situation 2, B2 is 10% lower higher, C2 is like 50% lower higher, some kind of story they will cook up. Okay. If you divide this by this, many of the terms will cancel and only one of them will be left out. This is a combination of ratio percentages and simple formulas that are shown up in all the core subjects. I think we already saw one example of that. Let me show you. Okay. This is very typical actually. Typical in speed, distance, time and all that. My cycle is 10% slower. I drive the cycle 10% slower. My speed of cycle is like 1/10 of speed of car. Right. Some kind of 2 scenarios they will cook up. Notice in scenario 1, resistance is 60. In scenario 2, resistance is 50. right? By dividing it, many of the unknowns got cancelled. Only one unknown remained, and you can find that, right? It was a two scenario question, kind of fits there. Okay, there are many such questions in a given gate paper, and this is one such example. In fact, this two scenario is actually, if a question is like kind of confusing, if you read it for the first time, you don't understand it, probably my area is it a two scenario question. Okay, this is certainly very, very confusing, so I'm not going to read it. So Hall effect flow meter is used to measure fine. Flow meter induces magnetic field in the fine. Caliper is used to measure vessel diameter. System calculated flow rate as 100 meter per cube per second. So let's get, they are talking about Hall effect. Epsilon as BLV. And this happens to be, we just notice this is BL Q over pi L square into 4. L is the diameter, right? This is what we have. You measure flow rate once, so you're measuring flow rate. Let's write it that way, okay? Some of these terms get cancelled. Q happens to be epsilon pi L by 4B, okay? So the system calculated the flow rate to be 100 centimeter cube per second using the known magnetic field, measure values of voltage and vessel diameter. After the measurement, all of a sudden the student realized calibration is performed, discovered that voltmeter was measuring 40% larger than the actual value. Voltmeter is problematic, caliper is problematic, right? So now
assuming
uniform flow, now that okay, you measured, you realize there is a mistake. Okay, can you go back and correct your initial calculation? Okay, so they are asking for actual blood flow. So this is scenario one, scape colors. Q actual. If you knew the voltage actual, okay, pi, let's say pi actual is like pi actual, okay, there is no like diameter actual by 4B actual. I think they are not changing the magnetic field. Some of the things are like held constant, right? Only there is an error in the voltmeter, the error in diameter. So the magnetic field, the same device, B doesn't change. Perhaps if you want to be slightly, if you want to like feel satisfied, you can put that act over there. Then you have scenario 2, Q, what you measured, some of these things are very different, right? Epsilon measured, okay, pi measured is still, I know there's a constant. Length measured by 4, B measured. You are not measuring B. Notice at the stage, yeah, if you're interested, you can put B measure, but you're not really measuring B, you're applying B. For that reason, these two magnetic fields are same, okay? I'm not distinguishing that anymore. What is known here, let's tick it off. Yeah, this, calculated, right? And some of the ratios. The ratios here and the ratios here. So let's just divide this to get some clarity, right? You have Q actual equals Q measured, Q actual by Q measured, right? I took that Q measured to the RHS into epsilon actual as epsilon actual pi L actual, okay? L divided pi. B 4B will get cancelled, pi also will get cancelled, so I'm not going to write it. This will be epsilon measured, that is given to be 40% larger than the actual value. So this is 1.4 epsilon act, okay? Again, there is a pi. I cancelled 4B by pi right now. I didn't cancel pi, I cancelled 4B by pi. I don't have space to write that. And then the caliper was measuring diameter 10% smaller than the actual value. So what it is measuring as 0.9 L act. Okay. Again, let's give it some colors so that we can see what is what. What I have here is, this is erroneous. This is measured as 90%. So 0.9 of L act. And then 10% smaller, 40% larger. So this is 1.4. 40% I am writing it as 1.4, okay? I hope you understand that. No issues there. Many of these terms will get cancelled. This right now, even you don't need to know, right? At this stage, notice the actual get cancelled. You don't need to know the diameter, right? Because it's a cooked up two scenario problem. So Q actual is Q measured by 1.4 into 0.8. Can we find what the actual is? And what units? Centimeter. Keep the, you get the answer in the unit that you put Q measured in. Just put in centimeter cube per second, 100 divided by 1.4 divided by 0.9.
79.36. Rounded off to 2 decimal places. 79.37. Yeah, this is 79.37. I just substituted Q measured in centimeter cube per second. I got the answer in centimeter cube per second. Okay. Everything else cancelled. Here, of course, I have the common sense to not find Q actual in SI and then convert it back to the required unit, because I know the unit that I want is a unit that is given in the question. Calculation is easier that way. Sir, you said always do it in SI and then find the required answer. There are many terms involved, many units, many variables involved. Here, one variable, it's given in the unit, required unit, just substitute that. Okay, fine. That brings us to now the end of this discussion. Okay, that brings us to the end of the first part. In this still working, that is still working. Okay, so that brings us to end of sensors part 1. I have to do cardiorespiratory. I'll do some part of cardiorespiratory. Okay, let me write down some important things. Hey, there is this one thing, right? Ls some constant mu n square E by n. Inductance, self-inductance is this. Temperature, we had two things. Temperature, we have R at a temperature is R0 into 1 plus alpha T. Okay. Then we also have RTA as RT, RB. R at temperature A is R at temperature B. E power minus beta. Okay. 1 by TB. 1 by TA. I use that ABBA. AB minus BA. Right. And then the sensitivity, dr by dt. This is minus beta by t square. And strain gauge and Wheatstone gauge. That's kind of real estate is a big issue. Okay, virtual real estate in a PowerPoint slide. So L is mu a square L n. Yeah, I have to write my mnemonic. Okay, yeah, thanks. Bye. And then this is strain gauges. Gauge factor is 1 plus 2 nu. And then we have relative change in resistances, G epsilon. And then we have output voltage as n by 4 G epsilon input voltage. Doppler, del is 2 cos theta U by C. F, this is C radian, and typically F lambda by 2 is D. Okay, this happens to be C by 2F, and this is C plus AT. That is one thing. And then for the HAL, we have epsilon as being ELA B. You can also write that as being ELA Q over A. Okay. Yeah, most of the things that formulas that you need summarized in one place. Okay, let's move on. Let's do some sensors is done. I didn't write down resistance, capacitance, and all that. Okay, it's a good idea to know some basics of that. Strain, Wheatstone, 4, Doppler, PCT, Hallstatt, cardiorespiratory, pressure, volume, lung, circulatory, blood gas. Okay, let's do some of this and wind up, and then can come back. Yeah, some of the sizes are getting too big. Just give me 1 second. Thus, which one of the following techniques makes use of Korotkovo? Okay, so this is biomedical engineers know this, doctors know this, instrumentation, electronics engineering students know this. Pressure measurement, they put this cuff spare that is known as big bow manometry, right? This is sound supposed to be heard in the stethoscope that is in the morning for Korotkovo sound. Okay, sigmometry, yeah. Audiometry, they are testing ear. Spirometry, volume measurements. Tonometry, tone, speech. What are they doing? Tonometry, tension, tone, something to do with eyes, I suppose. Tonometry, eyes. Okay, fine. Let's move on. During a non-invasive invasive measurement of blood pressure, mean arterial pressure is 1. So systolic pressure is this, diastolic pressure. Wait, yes. Have the pressure pulse as a function of time, right? No, walls are not leaking. It's just so this is the aortic pressure pulse, pressure inside the aorta artery, okay, major artery. Roughly, this is where your heart is pumping, and this is where your heart is filling. So you have systolic and you have diastolic. So we have this diastolic pressure, systolic pressure, mean pressure. Mean somewhere over here. Actually, mean should be somewhere over here, closer to best. So when they say this 120 by 80, they are referring to systolic and diastolic pressures. Here, of course, this is something else is given. I'm just, because this is most of you are kind of recognize this, 120 by mm, 120 by 80. And there, so here you have the systolic and the diastolic pressure. Roughly, let's also mark that, maximum, minimum, okay. What you want is a mean. Mean, you find it by a rule of thumb, okay. This is roughly 2/3 of the heartbeat. This is what is shown as a one beat. Next beat, this is roughly 1/3. So the mean pressure will be a weighted average of these two. The mean arterial pressure. So person is being rude, mean behavior. The arterial pressure rises up. That is a mean arterial pressure, right? Mean arterial pressure. Hypertension. So this is, this is mean, okay. Yeah, even if I say mean, there is an ambiguity there. Average arterial pressure. Roughly, this is weighted average between P systole and diastole. This is given a weightage of 1/3 P sys, and then 2/3 P dia. Okay. I suppose most of you quickly find out the answer. I'm not waiting for it. 75 mm Hg. If you directly take the mean, this is like, mean arterial pressure is given. This is given, and then this is given. They are asking me for diastolic pressure. I suppose 75, right? You didn't make the mistake, right? Can I take that for granted? Yeah. Okay, great. So, notice there is also something called P pulse. So, I don't know, in Tamil, pulse means something. I don't know how many languages teeth is referred to as pulse. Okay, so P pulse is this difference. P sys minus P dia. So, you can also write that MAP, okay, mean arterial pressure, as this is minus and plus. Yeah, this is 1/3 of P sys. P is, no, that is 1/3 of what you'll get is 1/3 of P sys minus P dia. So 1/3 of P pulse plus P dia. Okay. And add and subtract 1/3 of P dia here, you will get this. You get P pulse with the first term, second term completes, right? And you get this. So some basic relations, okay? So MAP, P sys, P dia, and also remember what a P pulse is. That's important, pulse. Okay. Person has a total blood volume of 5 liters. Out of this total, assume that 4 liters is consigned in the systemic circulation, 1 liter in pulmonary circulation. The cardiac output of the person is 5 liters per minute. Time taken for drop of blood to go from left ventricle to right ventricle. Yeah, this is where the circulatory system looks complex. Okay, but it's one tube. Now, total is 5 liters in this tube, circulatory system. Systemic circulation. They are splitting into systemic and pulmonary. Okay. Let's put, it's not deoxygenated, oxygenated split. This is systemic pulmonary split. So I'm going to use these two colors. Yeah, systemic, then you have pulmonary. Pulmonary somewhere starts at the right side. Okay. Let's say it starts at RV. Okay. Pulmonary artery. There isn't a strict divide. This is the right ventricle is somewhere over here. Ends at left atrium. And the lungs is somewhere over here. The heart needs some space. Rest of the body is over here. Is the rest entire body, okay? That's not a treadmill. That's the entire body over there. Lungs is over there. And then, so this is LA. Yeah, total is 5 liters. Every minute, 5 liters get circulated. How much time will take a drop of blood to go from here to here? So that 1 liter is cleared, right? What is there here is P pulmonary is given to be 1 liters. The systolic circulation given to be 4 liter, total is 5 liters. So if that entire 1 liter crosses, this drop will show up there, right? So now this becomes a very, very simple question. 5 liters corresponds to 60 seconds, that's a minute. So 1 liter, if this entire yellow color blood goes this way, that red color drop will start from there and end up here, right? This corresponds to 1/5 of 60 seconds. That is 12 seconds, okay? So the answer is 12. That's the entire person. Yeah. Perhaps we can make, that's the entire person. If you put it this way, you will think it's a head there. Yeah, the entire person. Okay, fine. 12. Fairly easy. Let's do 1 or 2 more questions. Theory question. No, hematocrit, plasma volume, lung volume. We have done some lung volume here. But again, I think I did some of those in HAP. Okay, what is hematocrit? A centrifuge, a thing of blood. Centrifugal tube, what stays at the bottom, mostly RBC. The percentage of that is HCT, hematocrit. Okay. And then there is this, yeah, I did this. Now the color is kind of refreshing my memory. That is that I have done this. Okay. It's not like I'm recalling this, that I have already discussed this in a video. So this is total blood, the straw color plasma will show up there, then this red blood cell, white blood cell. This fraction is hematocrit, HCT. Okay. That is given to be 52%. And assume the ratio of total blood volume in liters to total body weight in kg is 0.07. This is okay. This in liters and that in kg, if you put it, that number is 0.07. And blood consists of plasma and RBC only. So plasma and RBC. So they are forget that white line. Okay. There's only plasma and RBC, and RBC is 52%, slightly higher. Okay. At 52%. Plasma volume. What is the volume of the plasma? In a 70 kg percent. Let's find 70 kg percent. He will correspond to how much blood volume. They have given volume by weight. Supposed to be volume by mass. It's not volume by weight. Total body mass. Okay. Fine. They have given it in kg. We will kind of forgive them. Pardon them. So volume by weight happens to be 0.07. So weight is given. This is given. Can you find volume? That is 0.07 into 70. 4.9 liters. Great. So this is, I obtained that to be 4.9 liters. They asked us to guess, we would have guessed 5.5. 5, right? 4.9, they are given it. Now, 52% of this is hematocrit. So the plasma, what is left is 48%. Volume of that correspond to that will be 0.48 into 4.9 liters. This is the volume of plasma. Okay. And that happens to be, thank you, into 0.48. This is, yeah, all of us are on the same page. This happens to be 2.352 liters. So the volume of that hematocrit will be the rest. That will be 4.9 minus this 2.5. Okay. This hematocrit corresponds to this. In case they wanted, this volume is 2.548 liters. This volume you just obtained it to be 2.352 liters. Okay, now ventilation perfusion ratio, right? And then there is a question on lung volumes. Yeah, lung perfusion. And we need to, I have already seen a question on this lung volumes, blood gas. Then there was also some miscellaneous questions. Okay, let's kind of let's stop here, okay? One thing that would help here is, let's do some minor amount of homework for you. I already discussed the lung volumes. Make sure that you try to recall, find a means to recall, okay? Do that actively a couple of times. Do active recall. You can easily fill this up. I have given this. It is there. In fact, when you discuss HAP, I think we kind of did this, right? Yeah, we discussed this question. Refresh that. Pulse oximeter and all that I will do. Membrane announced this. Notice, till now, we haven't actually started with ECG. Typically, the bioinstrumentation is ECG, right? ECG questions will show up here. ECG, GPEG, and all that. Okay. So, yeah, we'll come back and finish this in the second part. This is fairly easily doable. There are some miscellaneous combination questions that I can actually afford to skip. Let me show this right away. We have already done this. You can say this is a question from biomechanics, or you can say this is a question from measurements, because we can answer this based on dimensions, or at the end of the day, you're measuring some things, right? This is a question from bioinstrumentation. Moyens Courtier. Biofluid question we have already done. Glomerulus, always kind of have a difficulty saying that. Glomerulus. Okay, glomerulus. Okay, fine. This is filtration we have done. This resistance circuit analogy with that. What is the resistance and all that? I did this, right? And I suppose I did this in biomechanics as part of biofluids. Okay. Cell is injected. Oh, this is a question on convolution. Signals and systems. Okay, let's skip that. And there is an op-amp based question. Yeah, if we decide to skip the miscellaneous questions, we have time to finish that in one more sitting. Okay. So this is a good place to stop. We'll meet again. And the next time is set, we'll kind of finish this. Okay. Second part will complete it. Come prepared so that it's kind of easier on that setting, okay? At least have the answer key and all of that, sure, so that verification is easy, okay? This is a good place to stop. If there aren't any other